Okay. All right. So this week really starts our trajectory into what we call model-based inference. So you're going to hear me refer to a statistical model a lot, or the regression model. Um, what does that mean? It means we're sort of trying to approximate a phenomenon. So, like again, maybe we're interested in, um, you know, relating. So for homework, one of the outcomes is cholesterol. The other one's BMI. So maybe we're interested in trying to figure out whether BMI relates to age or cholesterol relates to blood pressure. Um, Once we start adding more uh, predictors to the model, which we are free to do, um, what are we doing? We're actually saying we're saying there's a relationship in the universe between these variables, and we don't know the true nature of that mathematical relationship. So we're going to approximate it. We're going to model it. We're going to put a model together. And so the model is not supposed to be perfect. It's just supposed to be helpful to us. For example, there's a model of the universe that's similar to an atom. Right? The idea that, and you can kind of go both ways. The atom's like a little universe. Universe is like a huge atom where things spin around each other and so on and so forth. It's not a perfect description, but it's helpful to us. In the same way, the general linear model is a model in which we relate an outcome variable y to some linear combination of predictors that we call x. And one reason it's a model is because we're assuming that the relationship between the variables is linear, just like last week, that's approximated well by a straight line. It's very unlikely that these perfect linear relationships or even imperfect ones exist. Probably some other more complicated function that works, but the linear model is quite good at capturing the essence of the relationship. For example, we can understand the direction of a relationship. Does the outcome variable, right? Does cholesterol go up if someone tends to have high blood pressure that goes up? Or is it a negative or inverse relationship as cholesterol goes up, or as systolic blood pressure goes up, does cholesterol go down, so on and so forth, right? So it gives us at least a little bit of that. And the extra thing that we get to do is once this, we'll really see this in action next week. This week, we're going to have more than one X variable, but we're still kind of going to be in the world where we have only a single predictor. Next week, we're really going to see how we can improve our model by adding more predictor variables. And so we're still in the linear world because you see there's a bunch of plus signs and no squaring, right? Or no other crazy functions. That means it's linear. But the relationship ceases to be a straight line. It then becomes a generalization of a straight line, a plane in 3 dimensions, or once we go past 3 dimensions, we're in the domain of hyperplanes. So the model itself represents 2 things. The betas and the x values represent what we call the systematic part of the model, the thing that's doing the explaining. And then the epsilon, or the errors, represent the leftover. How much are we off by? And so, of course, as we talked about last week, our interest is in having the correct number of x values in the correct relationship to y to make the errors as small as possible. And so what this equation is saying is that we can predict or explain a given Y value, somebody's cholesterol, using a linear combination of what we call predictors, other things about the person or the context that they're in, their age, what sex or gender they are, racial or ethnic group, systolic blood pressure. We can continue to add more and more stuff, and we'll talk about that next week. It's mostly going to be the case that we never have all the stuff. There's going to be some leftover, unexplained part to the person's cholesterol, whatever it is. Again, we call that error or residual. And literally what this residual is this part of the model forms the predicted Y value that we saw last week, Y hat, right? And what Stephanie's question was, is how do we do this math? Well, if I have these betas, and so if these are numbers, so the betas are just end up being weights. How much do we weight each variable in the equation? They're multipliers. So to work out what a predicted value would be for somebody, you fit the model and you get these weights, the betas, and then you say, well, if somebody's age is 30, and they're male, you stick in numbers for the X's and you solve. So again, I'll go over that when we switch to SPSS. I'll open up last week's homework and we'll do an example there. So that's our prediction, and then the difference between that prediction and reality, the person's real Y value, is the error of the model. So last week, again, we discussed the least squares approach, which is a way to get beta values that make the sum of what we call the sum of the squared errors. The errors themselves will cancel each other out. So we square them and add them together as a measure of lack of fit. And so we try to minimize the total amount of squared error, which is proportional to the amount of error in our model. So we can do that in two ways. We can just add predictors until we're blue in the face, or we can study the problem and try to do that in a more systematic fashion. Last week, you dealt with a single X and a single Y. We're always going to deal with a single Y. Once we have more than one outcome variable, we're in the land of multivariate analysis, which we're going to not do in this course. So most of the time, we consider a single outcome variable at a time. And we try again to choose predictors that are substantively important, or prior modeling experiences has showed us to be important. And by important, there's lots of different metrics for importance. The p-value is one of them, and then we can start kind of comparing models. There's sort of and again, I'll talk about this in more depth next week. Regression models can give you very different results if you omit important predictors. And so that becomes a challenge, this sort of selection issue. How do you make the choice of what predictors should be in your model, so on and so forth. So that's where we're at. This week, all we're doing is we're just, again, this is a very flexible, broad system where we're just going to learn little bits at a time. So this week, our task is to figure out how to create values of these X's when variables are categorical. What do we do? Because we can do that. We're not stuck with age or systolic blood pressure or other continuous variables as our predictors. We can use anything we want. We just have to make them into numbers that make sense. So the main thing for this week is to understand what we're going to call indicator or dummy variables. And this is useful. This is basically one way to get categorical variables in a regression model. So what we're going to do is we're going to view this through a familiar lens, and then we're going to extend it to the regression issue. So just to talk about indicator variables for a second, what are they? An indicator variable is a numeric variable, a binary variable, in which we set up, it's essentially a column in your data set where if someone has a 1 on that variable, it means that they have whatever characteristic, or they're in whatever group is represented by the variable itself. Okay? So if you think back to the t-test example, we had Heather, who was interested in the difference between patient satisfaction across these two hospitals, A and B. So here, and so in t-test land, we didn't have to have the categories in any numeric form. All we needed to know was which patient was in which hospital. You compute a mean over those patients and a measure of variance, then you can do the t-test. For regression, we have to create a numeric variable because these x's do have to be numbers. They just don't have to represent numbers per se. So we pick a category arbitrarily. We're going to arbitrarily pick category A, hospital A. And if I had a full data set, I'd have a bunch of patients. I'd have a bunch of 1s and 0s in my column. Maybe I'd have an additional column that listed as a string variable the hospital, symbol. So a bunch of A's and B's. The way an indicator variable works, this one in particular, is you're going to have a 1 for anybody who's in the what I'll call the indicator group. The group in your data set represented by the indicator variable. They all get 1. Everybody else gets a 0. And we call the zeros the reference group. So an indicator variable differentiates between an indicator group and a reference group by a bunch of 1s and 0s. And note the name of this variable. The name of the variable isn't hospital, it's hospital A. And you can think of the 1s and 0s as yeses and nos. Right? So if a person has a 1, yes, they came from hospital A. If it's a 0, no, they didn't. So now there's other ways. We call this a numerical code. We told us a type of code, coding categorical variables by the indicator method. There's other ways to do this. We could have 1 and -1, 0.5 and -0.5. There's all different ways to code. This particular method is very useful because when we do it this way, we end up reduplicating the t-test. So just as a review, in the t-test world, so this would be our independent samples t-test, we got a test statistic which is a function of the sample means relative to this funky standard error term. Our hypothesis was that the two means were different, or the null hypothesis was that they're the same. Null hypothesis is that they're different. A large test statistic is evidence against the null hypothesis, right? The larger t gets, the smaller p gets. Smaller p gets, the less and less probable our results are if the null hypothesis is true. So notice we're not using any 0s and 1s here, right? This goes back to chapter 5. All we need are the sample sizes of both groups, the sample mean, and this thing called pooled variance, which is a function of the standard deviations of both groups of the variance. And so if we crank through all of that, we find that the t-value for the test is -2.08, representing the fact that there is a difference in mean satisfaction between the groups. For this particular problem, this t-test does pass our alpha criterion. The p-value is 0.048. And so we can conclude we have evidence of a difference between the two hospitals in terms of their patient satisfaction. in this particular situation, are we likely to be able to choose what hospital, to force someone to go to one hospital or not for the purposes of experimentation? Do you think that, does that sound ethical? Not really, right? So this is the realm of observational research. It's probably good to be able to do these tests. But when we do these simple mean comparisons, we're kind of implicitly making the assumption that there's really nothing else that differs between the hospitals besides, um, what they are. And that's likely not true. There's probably a lot of things, maybe about the patients, about the hospitals, that we might like to include as what we call a statistical control. And so again, I'll talk about that more next week. We'll see that in action next week. But that would be the reason why we might not be satisfied if we really want to model patient satisfaction. We might not be satisfied with the t-test. It's certainly not necessarily giving us a full picture of potentially why the hospitals might differ. It's also not helping us deal with any confounding variables. Can you think of any confounding variables, things that might be unseen in this problem but might affect hospital satisfaction in general, that aren't represented just by the name of the hospital?
Could be the type of patient that goes to the different hospitals, the kind of patient profiles.
Good. Could be like just the healthcare model, the care delivery that's done at the hospital, right? So we might like to know that stuff. And so it behooves us to think rather in terms of a linear model for patient satisfaction, which we then use a predictor called hospital A in that model. So here we're defining a linear regression model that ends up allowing us to test the same hypothesis. Right? Let's see how this works. Right? So we write down our outcome. Here we've got our intercept plus beta 1 times our new indicator variable, which, remember, anyone in hospital A, this hospital A variable is equal to 1. Anybody in hospital B is equal to 0 plus our random error. Let's see what happens when we take expected values. Right? So again, in t-tests, we're dealing with means, expected values. So in this formulation, the mean satisfaction for hospital A, we would find that by taking expectations of both sides of this equation. Right? You can see here, given that we're dealing with hospital A. So the way this works is, here's the magic. Our data point for hospital A, for a person in hospital A, is a 1. So we insert the 1, we multiply it by beta 1, and we have, because the expected value of these constants are just the constants. So that means if we take the expected value of patient satisfaction for just those in hospital A, it amounts to putting a 1 into the equation, and out pops out beta 0, the intercept, plus beta 1. The expected value of patient satisfaction for hospital B can be found by inserting the 0 for hospital B in the model, and out pops out the intercept. If we then take the difference between hospital A and hospital B, which, by the way, is part of our t-test, right? Our t-test tests hypotheses about the difference between the means of the hospitals. Okay? So we've just seen in regression land, how do we get those means? The mean for hospital A will be when we fit our linear model, which the data will consist of a bunch of patient satisfaction values in a single column of zeros and ones. If we put that into simple linear regression, we're going to get an intercept and a slope. The intercept plus the slope is the mean, the sample mean for group A, hospital A. And the intercept by itself is the group mean for hospital B. So then what is the difference between, so if we do mu A minus mu B, what do we get? Beta 1, or excuse me, beta 0 plus beta 1 minus beta 0. If we take the difference between this expression and this one, it's simply just beta 1. So what does that mean? It means two things. We now have two really interesting properties of this simple linear regression model with a single indicator. The intercept will be the group mean for the reference group, right? Because remember, our coding is that hospital B is the reference group, they're the zeros. So in using indicator variable coding, when we fit a linear regression model with an indicator variable alone, the intercept, beta 0, is the group mean for the reference group. And the slope for the indicator variable is the amount by which the reference group and the indicator group differ. It's literally that thing we're testing in the t-test. It's the difference between the group mean. Which is the same as it was last week, right? In regression with a single numeric variable, what does the slope term tell us? Anybody remember? The slope gives us, as we increase our predictor by 1 unit, right? The outcome increases by whatever the slope is. So if slope is 0.5, it means as we increase our x value by 1, the outcome increases on average by 0.5. So that still works, right? As we change by 1 unit of the indicator variable, which is from going from 0 to 1, what do we get? We get our change in the outcome. Right? And so all that's happening when we change here is we're changing groups. So as we go from the reference group to the indicator group, on average, beta 1 gives us how much we're changing. What's the difference between the two groups? So in the regression format, we've simply just reparameterized the t-test. We've changed the math behind the t-test, but we end up with the same result. So in general, we've reconstructed our t-test as a test of a beta coefficient in a regression model. And so our hypothesis test is that beta 1 equals 0. The alternative is just that it doesn't, right? So if the p-value for beta is small, means we can reject the null hypothesis. Now, some really interesting things will happen. What we're going to see if you run a t-test and a simple linear regression on the same data set, the test for the beta coefficients is also a t-test. And it's going to give you the exact same t-value, the exact same p-value. So it is literally the exact same test, just in a little disguise. Before we get further along, this is one downside to SPSS, although there's really no good solution to this in any statistical program. You have two choices when you have an indicator variable. You can store the variable as zeros and ones, but people don't often do that. And if you do that, it actually kind of wreaks havoc with the way SPSS works. And what I've read is that this is a holdover from the early days of computers, where 0 was like, you couldn't use that as a data value, right? So often you're going to see in survey data, so the PHMC data set and others, that one group is represented by a 1 and the other group is represented by a 2. And this actually is just it's so irritating. What SPSS does is it makes the way that we run it, there's a way to do it that you don't do it this way. But using the general linear model command, it creates the indicator and reference groups for you, or it creates a new variable unseen outside of your data set, given some rules about the values that it sees. So if you're using numeric codes for, say, a male-female variable, and you pass this as your predictor, SPSS is actually going to make female the indicator group, the reference group, and male the indicator group. What SPSS does is it uses the last or highest value in that variable as the reference group. If you have string data, it uses the alphabetically last. So if you had, instead of 1s and 2s, you had typed out male, female, male, female, male, female. And you use that, you pass that as the predictor to the regression problem. In the background, SPSS is going to change it to 0 equals male, 1 equals female. This matters because it's how you interpret the coefficients. And next week, when I do ask you to sub in values and get predicted values for particular types of people, this is going to matter. So this will make more sense when we look at SPSS, but I'm just kind of putting it in here now. So we'll see this in a little bit, but this is kind of just your shorthand. So when you have only the indicator variable as your predictor, in your general linear model output, beta, the intercept, is going to be the mean of the reference group, as I said. And then beta 1 is the difference between the two groups. So to get the mean of the indicator group, you just add beta 1 to beta. Now, it gets a little confusing, but you can ask for, and you should ask for, descriptive statistics with your output of general linear model, and you can kind of check yourself. You can peek at the descriptive statistics and then find the appropriate numbers in the regression table. So we'll see that once we get to our practice value. So the takeaway here, when we have a single indicator variable, is the intercept represents the mean of whatever we've chosen as the reference group, and we're free to choose that. It's pretty much an arbitrary choice, unless, what we're doing is sometimes also called treatment coding or a treatment contrast. So it's quite common to choose, if we were doing a very simple randomized control trial, to have the reference group be whatever the control group was, placebo, whatever. And then the indicator group is the treatment group, and thus beta 1 tells us how much better or worse the treatment group does relative to control. Thus we call it a treatment contrast. The indicator variable terminology is more general. Again, we're free to choose it. In a 2-group situation like this, all that's going to change is the beta is going to change. The beta intercept is going to be a different number because it's going to be a different group's mean, and beta 1 will change sign. We can play around with this later on. Okay. We are not limited to binary categorical variables in regression. In fact, that would be crappy. Um, so we're going to take a look at an example of where we might ordinarily use analysis of variance, which I've kind of skipped over to this point. So we'll talk about that in a minute. Analysis of variance was developed to really in the course of doing experimental work, where you have more than two groups, the t-test is not necessarily appropriate. And also, if you did a bunch of t-tests, it sort of wastes valuable type 1 error. You'll read about that. And it was very applicable in various areas of basic science. So here it is in an example that we might run into. So let's imagine we're doing a study on how prevalent childhood obesity is in different parts of southeastern PA. So let's say that BMI was assessed for young adults in the 5 counties in the greater Philadelphia area, Philly, Bucks, Chester, Montgomery, and Delaware County. Although there's lots of different things, racial, ethnic composition, built environment, economic status, even more, that we could study in depth, we're simply going to ask whether or not there's an overall difference between the counties in BMI. So without respect to any of these other variables, we're just going to look at the effect of the grouping variable county. So again, once again, we can retain these results by reparameterizing. But since we didn't go through what's called the one-way ANOVA, we're going to go through that first, very, very quickly, and talk about why the general linear model version is usually a little bit more helpful, but sometimes the ANOVA version is good too. Okay. How many, if you guys, I think you've all taken at least one basic stats class. So ANOVA should be somewhat familiar. The idea behind analysis of variance is we have a grouping variable that we consider as sort of a treatment or quasi-experimental variable. And instead of doing a bunch of comparisons between the group means, because we don't know like which one do we focus on, we ask a slightly different question. We say, is there a lot of variation among the groups relative to what we should expect if the groups were all the same? And so another way to say that is, do the group means vary a lot? So are the groups very different from one another in terms of their averages relative to how variable the scores are within each group? So if there's more variance amongst the group means, if the group means are spread out relative to how scores are spread out, then we make a conclusion, well, there's got to be some differences between the groups, some interesting differences. And so a null hypothesis for ANOVA is that given K groups, we usually use K to represent the number of groups or categories. The null hypothesis is that all K of the population means are equal. So in this case, county 1's BMI on average is equal to county 2, all the way out. This null hypothesis is true when this quantity, sigma squared, is our symbol for population variance. Remember, variance is just spread. How far spread out are the numbers that we have. Right? They all fall really far away from each other on the scale, or are they all bunched up together? So this null hypothesis is true when there is literally no variance. All of the group means are exactly the same. So what we do in ANOVA is we test this hypothesis against an alternative that says, no, at least one of the counties is different. So all we need to get variance to be an actual number is to have one of the groups to be different than the others. So here's the sample data that we have from almost 25, so 2,424 children. These numbers are actually percentile because the interpretation of height and weight is really dependent on how old the children are. So to make this a little bit fairer, all of the BMI values are converted to percentiles. So here's the average BMI percentile for Bucks County with a 95% confidence interval for Chester, Delaware, Montgomery, and Philadelphia. Note they all have slightly different sample sizes. There's more children from Philly. So our null hypothesis is that these numbers are essentially the same with just some noise. And our alternative is that at least one is different than the others. So we can obviously see they're all different numbers, right? Just like with t-tests or any of our other procedures, we have a burden of proof to meet, so we have to kind of make a decision. Are these numbers different enough such that this null hypothesis statement can just be abandoned? So again, one way to do this would be to test Bucks against Chester, Bucks against Delaware County, Bucks against Monco, Bucks against Philly, then Chester against Delaware, then Chester against Monco, so on and so on and so forth. If we do that, we get 2 raised to the number of groups, so 2 to the k. 2 raised to the 5th power is a lot. I don't remember what it is. It's let's see, 2. Oops. It's 32. So that means to fully test all the groups against one another, we'd have to compute 32 t-tests. And again, in your reading, you'll see that when the greater number of p-values, tests that we compute on one data set, the more and more likely we are to make a type 1 error. So this procedure, the analysis of variance, was created as a way to kind of first do like an overall test. Is this null hypothesis true or not, without doing those 32 individual tests? Now, it looks very weird, and I talked a little bit about this last week, but probably not very clearly. What you're looking at is the standard analysis of variance table that comes out with regression, comes out. We'll see it this week. We'll continue to see it with the general linear model. What you see so what this column is a sum of squares. Sum of square deviations are always differences between either, in this case, a group mean and the overall mean, or in regression, a particular y value and its predicted value, or in its mean. The formulas don't matter too much to us here. We're not memorizing them, or we're actually doing this by hand, but when you talk about what they represent sort of heuristically. This line in our ANOVA table represents an estimate of variation that is due to being in a particular group. So what we're sort of measuring here is variation amongst the group means. We call that between groups variation, source of variance. This represents what we call error variance, or basically the amount by which our model is off. In ANOVA, it represents simply a sort of a weighted average of the variance inside each group. So we take a sum across the sum of squares in each group, and we divide by the number of people total minus the number of groups. So this gives us basically a pool, like pooled variance kind of thing. So the F statistic, the F test for analysis of variance is a ratio of two variances. The one on the top is the variance in BMI that can be attributed to what group you're in. And the one on the bottom is the variance in BMI that doesn't have to do with, well, it's the variance that has to do with what group you're in plus all of the random stuff. And we make a decision about our null hypothesis based on this ratio, F ratio. So again, the numerator, the top table, the between part of the table, we're simply estimating BMI variance in a particular way based on being within a particular group. The bottom, we're estimating BMI variance without respect to groups. And so if there's a lot more variation in our data that's explained by the groupings, then there must be an effect. There must be some difference between the groups, some systematic difference between the groups. Now, in regression, the F ratio is also used to test the overall prediction model, where again, the numerator is an estimate of variance of the outcome that's explained by the model, and the denominator is an estimate of the outcome variance that's not explained, the error. So we can use it in both cases. The F distribution is skewed. It's also got 2 degrees of freedom values, which I kind of zap you with in the quiz. You'll get used to that, and we'll walk our way through it. We'll navigate it again this week. But it's a one-tailed test. The larger that F gets, the more and more surprising it is under the null. And again, if we look at it, what does that mean? The larger and larger F gets, F's going to get larger if the between groups estimate is large. The between groups estimate is going to be large if the grouping variable has an effect, right? If the grouping variable has an effect, right, so the county affects BMI, then at least one of the means is going to show that. You're going to see differences among county. So the chain of logic for ANOVA is a little bit long. But if we go from the beginning, right, okay, if the null hypothesis is true, there's no variation among the group means. We can compute a measure of variation from our data using sum of squares, change it into a variance, do the same thing, a second estimate that doesn't have to do with groupings, put that on the bottom. That constructs our F ratio, which is a single number. We test that number against a cutoff, or we compute the p-value, the area beyond it, and compare that to 0.05. And the final thing that we always need to report are the degrees of freedom of the F test. So let's, here's how it works in with a single grouping variable. So in this ANOVA situation, the first number we call the numerator, or between groups degrees of freedom, is k minus 1, the number of groups minus 1. Another way you can think about that is the between groups degrees of freedom for an F test in this situation is going to be the number of equal signs in the null hypothesis. How many equalities are in the null hypothesis? So let me write that out, right? So if we do, I'm not going to type the muse, I'm just going to say Philly is equal to from the Bucks equal to Cal equal to Chester and the Delta, right? So I've got 1, 2, 3, 4, 5 groups. 1, 2, 3, 4 equal signs, 4 degrees of freedom in the numerator of this test. The denominator degrees of freedom, or within groups, or error degrees of freedom, is the number of groups, and we take that, which is 5, and we subtract that from the total degrees of freedom, which is just n minus 1. Another way we can think about that is the within groups degrees of freedom is simply n minus k. And so in this case, our total sample size is it's actually 24, 24, I believe, right? Oops, let me turn off the annotate. 24, 24. We've got 5 groups. Whoopsie. Go back in. So equals 24, 24. df within equals n minus k. K is 5, so that's 24. 24 minus 5 equals 24 here. So we always report these 2 degrees of freedom values. The one we see in the between groups line, it looks a little bit different in SPSS, so I'll use that terminology when we get there. So if you report an F test, you're always reporting 2 degrees of freedom. Why are we doing that? The F distribution just so happens to have 2 degrees of freedom parameters. The T distribution has 1, the F distribution has 2. Okay? The main reason for that is because, so chi-square distribution also has 1 degree of freedom, right? If you recall that from chapter 5. The F distribution is a ratio of chi-square distributions, each with their own degrees of freedom. And so that's why we have 2 degrees of freedom. So all the degrees of freedom do for us is they just define what actual shape we have here. So they help us, they make it possible to compute the p-value. They identify a particular F distribution. So just like with T, there are in chi-square, there's an infinite number of different F distributions with slightly different shapes. They all look generally like this, just they're sort of stretched or compressed on the x-axis, and the degrees of freedom index them, basically, the parameter that kind of controls that shape. All right, so if we had done an analysis of variance, a one-way analysis of variance, we might get this result. We get an F value 9.858, which corresponds to a very low p-value. And what we're allowed to do is we could say there's strong evidence that the mean BMI percentile of children differs in at least one county. So a downside of ANOVA, and in general, this is an issue, this is what you're going to read about in that article, is now that we've done that, we've simply just done our initial test on this data set. We don't know which groups are different from which other ones, right? So again, we can make some guesses. We can say, oh, they're all really different. One thing we can do is look at whether their confidence intervals overlap, or really whether the mean of, say, Bucks County falls into the confidence interval for Chester. And that's another thing we can do. If it doesn't, then we can say that they're really different. But we have a more automated set of procedures that we call post hoc tests. As you'll read about in the article for this week, Post hoc tests are modified P or F tests. They're performed after you know the results of an ANOVA, and they're modified to keep what we call the family-wise error rate at 5%. So we talked about alpha a lot at the beginning of the course. When we test the hypothesis with an alpha of 0.05, again, what we're implicitly saying is we're saying we're going to use a level of evidence such that we retain a 5% chance of a type 1 error when we make our decision. If we did 5 t-tests, right? Oh, right, it's not the number of permutations, it's the number of unique combinations. We'd have 10 tests to run, so not 32, but still a lot. Right? If each of those is conducted with a 0.05 alpha, we'd actually have an overall type 1 error rate of 50%. Right? So if we run 10 t-tests and we don't adjust alpha, we don't adjust for multiple testing, our type 1 error rate balloons. So we're now have a 50% chance that if we make at least one type 1 error. So you can read about the history of post hoc testing. It's become kind of a cottage industry. There's no one right way to do it. We're going to use the Bonferroni procedure, which is actually a little bit different than the one in the article. It's an automated procedure in SPSS. So I'll show you what that looks like when we get there. So if we did an ANOVA on these and we did post hoc tests, we would find the following. This first sentence summarizes the results of the overall analysis of variance. And we did a one-way ANOVA, and we found that there was strong evidence that the mean BMI percentile of children differs in at least one county in the Philadelphia region. Why do we do that? We can say that because our F value is large, P value is small. The rest of this is all the result of our post hoc testing. So all we're doing here is we're going through in a systematic way and reporting which counties, based on the post hoc tests, were truly different. So it says post hoc tests showed that Philadelphia County, here's its mean confidence interval, had a higher mean BMI percentile than Bucks, Chester, and Montgomery. Right? And so for each one, we see the mean for Bucks, confidence interval. This is the p-value for the post hoc test comparing Bucks County to Philly. Right? Here's the p-value for comparing Chester to Philly, and the p-value for Montgomery to Philly. Then we go on to say there was also evidence of Delaware County having a higher mean BMI than Chester County. This is just one way we could have said it. You're going to see what we get in SPSS is we get a table of all of the pairwise comparisons, all of the two group, right, Philly versus Bucks, so on and so forth, that are possible in our data set. We look through to see which ones have the small p-values, and we try to construct a paragraph like this that's sensible. So what Dr. George did here, who wrote this, is he noticed that Philly tended to be significantly different than almost every other county. So you organize the sentence based on that. You say, oh, okay, Philly, here's its mean and confidence interval, is higher than Bucks, Chester, and Montgomery. Also, you would notice that Delaware and Chester County were different. When you're reporting post hoc tests, we don't exhaustively report the tests that don't turn out to be significant. We just report the significant differences or the low p-values. Right? So when you're reading about post hoc tests or you're writing one up, if you leave out a group comparison, so notice we don't say anything about Bucks versus Chester County. Implicitly, by leaving that out, we're saying those two groups didn't differ. So that was analysis of variance in a nutshell. Usually when I would teach undergrad stat, that'd be a whole week because you'd have to learn how to compute it, which was silly. So we will, though, we're going to, this week you will have to perform an ANOVA, so I'll go through it in our SPSS practice in a little bit. Okay, so we'll take our break, but beforehand, let me just review a little bit, right? What have we learned so far? We've learned that we can use a regression model to mimic or really reproduce a t-test. And I've now kind of, because we didn't do it in week 4, sort of laid out how analysis of variance works with a grouping variable. When we come back from our break, what I'm going to do is show you how we put this into a regression model. And it's very, very similar to the t-test. And then we'll go ahead and actually poke around in SPSS and see how these work. Okay. All right, so let's do 10 minutes. We'll come back and finish up. Okay, good. All right. So again, our final challenge is, can we get the same result as we just got using a regression model? And the answer is yes, we can. With one kind of, this is sort of a downside of when we have categorical variables with more than 2 groups. One thing we don't get in the regression equation is that overall test, but we can still do it. It's still doable and it is an F test. The next week, when we combine, we have models with numeric and categorical predictors in them, we're going to see that SPSS will automatically conduct the appropriate F test for any categorical variable. And indeed, it will conduct it for any numeric variable as well. So we'll discuss that next week. It will come out this week too, and I'll show you how, again, you'll get the same numbers using regression versus the ANOVA command when you have a single categorical predictor. Okay, so the way this works when you have more than 2 categories is, again, you have to arbitrarily pick a reference group. Okay? Just arbitrarily, doesn't matter. In fact, it kind of does. So here's, again, the indicator variable approach, AKA the dummy variable approach. It's another word you'll hear used to describe it. Again, is also known as the treatment contrast, which refers to the tests that the individual betas will give you. So again, if you have a natural control group or comparison group, so let's say, we were doing a very purposeful comparison between Philadelphia and the 4 other counties in the region. And so our part of our research question was, are children in Philadelphia, suffering from obesity, right? Are they more obese? This would be a really great coding to pick. Take a look at what I've got in this equation. Remember, we have 5 groups, but when we use indicator variables in our regression model, we'll have 1 fewer beta, right, or slope. The final group, the reference group, is absorbed into the intercept. So what you see here is we've got BMI percentile is going to be a linear function of the intercept, some effect of being in Bucks County, some effect of being in Chester, some effect of being in Delaware County, plus some effect of being in Montgomery County, plus random error. So we've left Philadelphia out of the equation. Why? We can't include it in this particular version, or else our solution is what we call underdetermined, meaning that it's the numbers, basically the results won't converge. It has to do with matrix algebra and all this stuff. But it's also not necessary. You don't need it because remember, it's analogous to what we had with hospital A versus hospital B. One of the parameters does represent your reference group. It's the intercept. It's going to represent the mean of whatever the reference group is. Then each beta is still going to represent a difference, but we work it out this way. So again, we take expected values for conditional on the values of the indicator variables. Okay, so now follow me. There's a lot of symbols here. Okay? Actually, I think it's helpful. Let's do something quickly that I always forget to put into the slides, but if you'll indulge me, we're going to actually build the table right now. Let's see, we'll have 5 columns. We'll make 10 rows. Okay. So this will have person, oops. 1, 2, 3, 4, 5, 6, 7, 8. All right. Let me add 1 row here. Column. 1 column. Okay. So this might be how we would, and you know what, we'll might as well just do this too. Let's just imagine. Yeah. Six. These are the BMI percentiles of the kids, showing you what these data might look like. These are just, I'm just making these up now. Okay? So when we have a variable like county, what SPSS does in the background is it looks at this variable in SPSS, and we might have a 1, 2, 3, 4, 5 coding or something like that, right? Any coding will do. Strings, doesn't matter. What SPSS is going to do in the background is, if we've chosen to code with Philadelphia as the reference group, we're now going to make dummy variables or indicator variables for Bucks, Delco, Monco. Oops, I always forget Chester. We'll do it in alphabetical order. So the way we enter this into the regression model is we have these 4 new dummy predictors. Okay? Somebody who lives in Philadelphia County, and indeed all of the counties are represented by a pattern across the 4 new dummy variables, not just one of them, right? So in order to code for Philly, we need these 4 columns, and they all need to be zeros. Okay? So a kid in Philly is going to have zeros for all of the predictor values of the indicator variable. Bucks, we're going to have a 1 there, 0, 0, 0. Monco. Okay. So as we can see, the Bucks County variable index is, right? We got a 1 if you're in Bucks County. If you're in any other county, you're a 0 on that. Chester, similarly, we've got all zeros and then ones for the two Chester County people. Delco, in this smaller bridge version, we've only got one person, so we see the one there. Montgomery County, we've got two, right? And then Philadelphia is represented, right? We don't need another column for Philly because we know who the Philly people are because they have zeros on everything, right? So it's a pattern. That's what I mean by the ones and zeros here. So again, SPSS, you store your data this way. In the old days, you actually had to make these additional columns, these ones and zeros, and pass them. But you don't have to do that anymore. You can store your county variable in one column, and depending upon the way you code it, SPSS does this in the background and enters these variables into the regression equation. Right? So if I had one column with five possible categories in it, and I run a regression, my regression is going to pop out with 4 new predictors. Right? So again, the pattern for Bucks is a 1 in place of Bucks, 0, 0, 0. And so the mean BMI for those in Bucks County is intercept plus beta 1. Similarly for Chester, the patterns is now 0, 1, 0, 0. So that picks out beta 2 as add that to the intercept to get the mean for Chester. Delaware County, it's beta 3. Montgomery County, it's beta 4. Right? And then of course, here's the important part. The intercept in general in a regression equation represents what is the average value of y when all the predictors are equal to 0. So in the indicator group pattern, when all the predictors are equal to 0, that's your reference group, Philadelphia, right? Has 0 on all of the county indicators. And so the mean for Philly is represented just by the intercept by itself. And then as we did before, we can then go ahead. So if we want the difference between Philly and Bucks, we take the appropriate differences there. So we have the option to do post hoc tests in here too. We can do all kinds of stuff. The regression model output for these indicator contrasts, so the actual betas, are sort of incomplete. Sometimes they're helpful, sometimes they're not. So depending upon your goal in the analysis, you may, if you have a variable like county, it may be more informative to look at the F test of overall, do the counties differ, versus looking at any particular beta, right? Because the way that we've now encoded this problem and reparameterized it, the intercept is the mean of the reference group. That will always be true, or the mean value of y when all the predictors are equal to 0. So that represents Philly residents. This indicator coding sets up what we call these particular contrasts. A contrast in regression is just a group comparison, right? So it sets up these treatment contrasts where the betas represent the difference between each subsequent group and the reference group, and that's it. So if we only had one, if we had just one beta, so we had a binary categorical variable, the intercept represented the reference group, beta 1 is going to represent that important mean difference that we care about. When we have more than 2 groups, the betas are kind of, sometimes they're helpful. Again, if our goal in this study was to compare every county to Philly, then these betas are exactly what we want. That's not always true. So sometimes, this is just kind of a cautionary tale. Sometimes when we put categorical predictors, what we're going to start to call factors, is another thing in the ANOVA language. We call these factors. When we start to put factors into regression models, the betas aren't always helpful. And so we use them in regression models because sometimes we might want to control for county of residence when we're really looking at the relationship between BMI and, is the person on food stamps or something like that, right? So that's why it's important to be able to include them. The betas may not always be central to your research question. So again, we'll talk about that in a second when we look at SPSS. Another thing to note, beta, what we've been calling beta coefficients are really what we call unstandardized regression coefficients. Unstandardized regression coefficients are, they can be all kinds of different magnitudes. They're on the scale of measurement of the outcome variable, right? So how many units of the outcome variable change when we change the predictor by 1 unit. In some situations, it's helpful to standardize coefficient estimates so that they represent effect sizes. We're not going to do that in this course. But SPSS will give you standardized regression coefficients sometimes. So you can just ignore those. We're going to use the unstandardized coefficients. They're more interpretable, but Greek letters can't, as sort of mentioned this in the video last time, SPSS can't represent Greek letters, so it uses a capital B for the unstandardized regression coefficient. So there isn't like a standardized terminology, no pun intended there, for regression estimates, but we're going to call them betas or unstandardized coefficients or whatever. So just don't get confused when you look at the literature. Sometimes these things are used interchangeably. So yeah, it can be a little bit confusing. All right. Well, let's dive right in. I can re-upload these slides so you have this this thing that I always forget to add, and now I've added it. But let's go ahead and switch over to SPSS. I do want to address, I'm trying to find the problem, the homework problem. Let me pause this for a minute. Okay, so first one, this is an important one, especially for situations in which your coefficients are really, really tiny, right? So a coefficient is, right, again, the standard interpretation of a regression coefficient as it comes out of the output is it's the amount by which y changes when we change x by 1. Okay? So here the regression equation was, crap, I forgot what it is. So why don't I have the answers come out here to rerun this? I have it somewhere. Oh, this is week 6. And
We should be able to figure it out based on the answers down below, right?
yeah, but I'll just bring it up. So the regression equation for cholesterol was intercept is 120.587 plus 0.331 times systolic blood pressure. So the the question is, okay, that's a change of 0.331. Oh, go away. In systolic blood pressure isn't super meaningful. How can we make it meaningful? So again, changing 1 unit systolic blood pressure leads to a change in cholesterol of 0.331, which is a very small change. And indeed, 1 unit change in systolic blood pressure isn't a very large change either. We are free to change the units by which we work by simply multiplying, right? So if I want if I'm interested in what happens if systolic blood pressure, aka the predictor, changes by 10 units rather than by 1, I multiply the regression coefficient by that number, by 10, right? So in this case, I just move the decimal point over to the right. And so for a 10 unit change in systolic blood pressure, the amount by which cholesterol would be expected to change is 10 times the original estimate. So it should be expected to change upwards by about 3.3 units. So this is helpful anytime you've got biometric data or you have really small coefficients. This only works obviously if your predictor is numeric. This doesn't make any sense if you have a categorical predictor. But for numeric predictors, if you're interested in a greater amount of change, you just multiply the beta value by that number. The second one, what do we do here? Well, this is why I have you write out the equation. Right? So we have our equation. I'm going to go ahead and just type it out here. Of course I can't. Let's move you over. Here's our equation. So expected value of cholesterol given x equals 120.57 plus 0.33 times SBP1. So when I ask you what would the estimated cholesterol be for a hypertensive patient with SBP 140, I'm giving you now that value of systolic blood pressure. So all you need to do is put that in the equation, multiply by 0.33 and add. So that would be here, 20.587 plus 0.33 times 140. That gives us, obviously you can see the answer, but let's work it out. Gives us 140 times 0.331 is and then of course add those together and you get a result that's in this range. So that should be 166.429. So should be about 9. What did I say? 9, 2. Yeah. So this week you won't have to do this because it's kind of moot with categorical variables, right? In general, when you only have categorical variables, you're not going to have like differing values. You're just going to have ones and zeros. But the following week, you will do it. I'll give you values of all the variables. Say, okay, so in that week, we're going to be trying to predict cholesterol with not just systolic blood pressure, but a bunch of other stuff. So I might say, well, what's the estimated cholesterol or predicted cholesterol for a patient with systolic blood pressure of 140, who's male and this age? And all you do is you take the equation you wrote out and you pop in these new numbers I'm giving you, and you just multiply and add. So sorry I didn't mention that. Stephanie, apologize that you had to figure that out online while you were doing stuff. But did that cover it?
Yes, thank you.
Yeah, no problem. I think that was, did we do, was there another one? No, those were the only two there. So, and if you run up on stuff like that, so hopefully that didn't cause you too much trouble. But if there's anything ever on a homework assignment that you don't understand or you think I didn't go over, just go ahead and email me and ask me. So what you're going to do this week is we're basically just going to kind of explore this relationship between t-tests and regression and ANOVA and regression. So let me get our practice files open. I'll just open them on my computer. You can find these on Blackboard. So it's the same. We're going to, just like the homework, we're going to use the same practice over and over and over again. Same data set. I believe we used this last time, APOE. Our outcome is BMI. So I'm going to do a couple of things. I'm going to show you how, a little bit about ANOVA. There's no t-test review here, but we'll review that and show you how these results come up. So we'll start with ANOVA. What we're going to do is we're going to run an analysis of variance on BMI across the APOE genotype groups. Right? So just to kind of, I think it's easier to sort of take a look at what we're looking at, right? There's 3 different genotypes, the E2, the E3, and the E4. So our null hypothesis for ANOVA would be that they're all equal to one another. Right? So that's 2 equalities. We know we're going to have a F test with at least 2 degrees of freedom in the numerator. Here's the means. And in fact, we have our F test results. Let's go ahead and get those out of SPSS. Now, I'll make this a little bit smaller so you can see it a little bit better. Okay, so here's our variable of interest. For ANOVA, it doesn't matter how it's coded because we don't care. It's just group means, so on and so forth. So the analysis of variance, we call it a one-way analysis of variance if there's just one grouping variable, as we have here. And we can find that menu in the compare means and proportions menu of the analyze tab. Okay? It's right here as one-way ANOVA. So first we're going to do it as a one-way ANOVA. And you can actually do one-way analyses of variance on multiple outcomes at the same time, but we're just going to do one. So just like everything else, SPSS is like different. Each menu looks different. So the outcome is the dependent variable. The numeric part of ANOVA is always the dependent variable. In this case, it's BMI. And our factor is, why is it not here? It doesn't work. Oh, it's because it's a string. I've never seen that before. I think this is new. Oh, group, right. So I forgot about that. So one thing to note is that string variables will work in regression, but not in one-way ANOVA. So we've got APOE genotype as a string, and then a reduplicated as group. No, nope, that's not. That's a different friggin' variable. Oh, I forgot about this. Okay, I have to post a different data set for y'all. I'm going to go ahead and add a variable. API num. Oops. Ugh. All right. That's annoying, but now we're back to business here. Ugh. Okay, so APOE is our factor, which apparently can't be a string variable, and BMI is our outcome. I want to clue you into two things. So generally, we would wait and do post-hoc tests until after we did the ANOVA, but it's usually helpful to just have SPSS do them in case you need them. So there's a post-hoc tab, and we want to click Bonferroni. That's the one we're going to use. As you can see, there are so many different types. People argue over what's better. They differ in terms of how conservative they are. Right? So how much do they adjust the bar for deciding about the null hypothesis? Some are a little bit more conservative, meaning greater type 2 error, less type 1 error, so on and so forth. That's the trade-offs. Bonferroni is a nice kind of middle of the road one. We also have some options, which include fixed or descriptive statistics. Always a nice thing to do to get those. So post-hoc and options tab, those are helpful. Click OK. And as we see, we've got the means of our groups, which should be the same. If you look on the, yeah, they're the same as the PDF from the practice. Okay, and we've got slightly differing ends in each group. And here's our F table. So our F table in ANOVA is pretty simple. We've got the between groups variance, mean square. Within groups, our F is very small, so it's actually less than 1. And our p-value is denoted by the sig box, is also very small. So we would look at this result and say we don't have any evidence for a difference in BMI across the genotype groups. Now, because of that, you can ignore the ANOVA effect sizes. Well, they're used, but not in this course. Right? So because this is not a significant result here, or we don't have evidence against the null, when we look at our post-hoc tests, we see sig, the p-values are all equal to 1.0. So that's going to be the case generally when, so post-hoc tests really are not appropriate here. They're appropriate in the sense that, you know, you could do them, but we would say they're not appropriate because there's nothing to find. They only help you out if the null hypothesis of ANOVA is rejected. Just to take you through what this table does, I haven't labeled, let me rerun this. Let me quickly add some data labels so this looks a little bit more helpful. Okay. E2, 2 is E3. So now we can see the groups are labeled. Right? So what this table gives you is, here's the difference in BMI between group E2 and E3. Right? So it's pretty small. There's a standard error for it. The mean difference divided by standard error will give you a t value, and this is the p-value. We also get a confidence interval for the mean difference. And so just like a t-test, if this mean difference, if the confidence interval for the mean difference doesn't contain 0, significant difference, so on and so forth. These tables are redundant in the way that a correlation matrix can be redundant. So we have E2 versus E3, which is the same information as E3 versus E2, just the sign is different. So when you look at a postdoc table, there's only a few of the rows are actually relevant. The rest of them are duplications of the same thing, right? It doesn't matter which order we test the means in. All that matters is the unique combinations. So it's actually the case that when you have 3 groups, there are only 3 unique comparisons. We see them here, E2 versus E3, E2 versus E4, and then E3 versus E4. So there have only been 3 p-values we would have cared about. 4 groups, it increases to 6. 5 groups, 10, so on and so forth. It gets larger and larger. So just be aware of that. Okay? So from ANOVA, we can ask for descriptive statistics. The analysis of variance is an F test, just testing the null hypothesis that all the group means are equal against the alternative that at least one differs. If we reject the null hypothesis, we can get further information about what specific groups differ from all the others by looking at the multiple comparisons. In this situation where we have no evidence of group differences, that's borne out in the multiple comparisons table too. Okay. So let's see what we get if we do this in the regression format in the general linear model. We're going to compare the output. So now we go to general linear model, just like last week, univariate. The difference, okay, for this week, and we'll carry it over to next week, is last week you used the covariates box, which is true when you have numeric predictors. You put them here. I happen to have a categorical predictor, which we'll call a fixed factor. SPSS refers to these as fixed factors. Even though I'm using numeric codes, it's still categorical. I put it there. Okay? So categorical predictors, which we also call factors, go in the fixed factors box. This week, we're not going to have more than one. Just like last week, we're not going to have you're not going to use more than one of these boxes. Starting next week, you will. Okay? So this week, you're going to have, for your 2 different data sets, you're going to have a fixed factor to move over here. You're going to have a dependent variable to put up there. Okay? And there's not much else you need here, although there are some helpful things. So first and foremost, you can get post hoc tests for factors this way. Okay? We can move them there on Frony, so I can get the same post hoc tests as before. Another thing that can be helpful and will be important in week 8, and I'll go over it again, is you can save things from this model. You can save predicted values and residuals. Right? So you can instead of computing predicted values, you can actually have the computer do it for you. So I'm going to do that just to show you. They're not helpful this week. And then in options, it's always nice to get descriptive statistics again. Oh, one more important thing, right? Descriptive statistics, and don't forget, we need our parameter estimates. That's the whole purpose of doing it this way. Parameter estimates gives us our regression equation. That's in options. So let's do that all again. So now we're going to do one-way ANOVA in the regression paradigm. Our dependent variables BMI. We have a single categorical variable, fixed factor. We will ask for post hoc tests for that factor. And we'll go ahead and save the predicted and residual values, and then options, parameter estimates, descriptive statistics. Okay. So here's our univariate ANOVA, which it actually calls a univariate analysis of variance. Because that's kind of what it is. We get the parameter estimates for free. So we get a lot of the same information. Our table looks a little bit different. Okay? The table is going to get more, the F table is going to get more complicated as each week progresses. For this week, we'll notice that there's two rows that look exactly the same, this corrected model row and this row that says APOE. And those numbers should look familiar to you. They're the same numbers that we got from the one-way ANOVA. So SPSS will compute and report the F test, the overall F test for any factor, which can be super helpful because if you haven't done the analysis of variance, you've just put it in the regression model, this sometimes can be a better piece of information for inference than the beta coefficient, because this is going to tell you, okay, is there some effect of that categorical variable in general? Whereas the beta coefficients, remember, are testing particular differences between the groups. Now, just like last week, in your parameter estimates table, you've got a few numbers. We've got an extra one, and then you see this 0. It says this parameter is set to 0 because it's redundant. What SPSS is telling you is that it's made group 3 the reference group because you don't need it. And again, what SPSS does is it makes whatever numeric code is the highest, that becomes the reference group. And so let's take a look at what the estimated, first, the sort of regular standard regression equation is and the estimated one. So this is what our equation is based on how SPSS will handle this variable, right? Group 1 represents E2, group 2 represents E3, group 3 represents E4. That's the last group. That becomes the reference group. It's left out of the equation, right? It's absorbed into the intercept. So our regression equation is going to give us an intercept value, which is equal to the mean of the E4 group, a beta 1, which is the difference between E4 and E2, and beta 2, which is the difference between E4 and E3. We also get a few different hypothesis tests in here. The ANOVA hypothesis is a joint test of beta 1 and 2 both equaling 0. Each beta has its own individual test. Okay? So the joint test is represented by the F test. Okay? So this F value of 0.156, large P, is a joint test of whether or not these two coefficients are different from 0. Right? And so we see up here that the test fails. And indeed, if we look down here at each one individually, these are two individual t-tests for the predictors independent of one another. Reading off the table then, our estimated equation is going to be the intercept. So we can, BMI will be a function, even though it's not significant, we'll use it as an estimate. It's not going to be very good. BMI is equal to the intercept 25.343 plus 0.149 times E2 minus 0.46 times whatever the value of the E3 indicator group is. So we'd see it there. So what you can start to think about now, now we have basically, even though we've got conceptually one variable phenotype, the regression equation has two predictors. And you can start to develop this understanding of the predictors and the coefficients as being sort of adjustments that are made. You may have seen this in research articles that say, well, these are adjusted odds ratios or adjusted coefficients, so on and so forth. You can think of that in the following way. This equation represents sort of like a default estimation for BMI for one of the groups is 25.343. If we want to get an estimate for a different group, we adjust by these values depending upon whether the person's in that group or not. Similarly, if these were numeric variables, we would adjust by that amount based on what the person's value of that variable was, age, systolic blood pressure, so on and so forth. So in the regression model, the intercept always represents a mean value of some subset of people in your data set. And then the coefficients and the grouping variables then just represent how do we move things around given this other information. Now, in this situation, this is essentially an equation for random noise, but we can still use it as a sort of a learning tool. So any questions on the sort of the differences and similarities between ANOVA? This is one thing I should have noted is we do have some assumptions of regression, which I'll go over in a later week about the residuals themselves. So that's what this part is, but we can skip over it. We're not going to deal with that now. We're going to kind of bundle that all into 1 week by itself. All right. So one more thing, I want to just kind of, it's not part of the practice, but just to show you, because you'll do it for homework this week. Just like with ANOVA, we can do the same thing with a t-test, sort of show that it's equivalent. So let's see, I think sex. Right, so we've got male, female. Okay. So what we're going to do is we're now going to look at, is there a difference in BMI from males to females? And we'll do that using the t-test interface and then regression. So just to review, this would be an independent samples t-test. Our test variable is BMI. Our grouping variable is sex. And remember, we have to do M. And click OK. And see that, first of all, Levine's test for equality of variances, everything's good there, so we can use this line. We get a t-value of 0.826, degrees of freedom of 78. The two-sided p-value is large. Estimated mean difference in BMI between the groups is 0.75, confidence interval there. I can get the same information out of the regression interface. And indeed, just like before, where you see an F value reduplicated, we'll see that the t-value shows up again. So let me show you that. The sex is going to be my fixed factor. BMI. I need to get my parameter estimates, and we'll dispense with the rest. So here I've got, okay, so here's, and this is a good lesson here, right? So with string variables, the alphabetically last group is the reference group. So male becomes the reference group. So this becomes an equation for BMI using female as the indicator variable. Notice the sign is negative here, right? Representing the fact that if we looked at the descriptive statistics up here, males tend to have a slightly higher BMI than females, right? And our estimate up here was 0.75 in the positive direction. The only reason for that is, in this case, I designated M as group 1, and SPSS does the t-test difference 1 minus 2. So I get a positive number here, and I get the same negative number here because now SPSS has flipped it around. M is now the reference group, and the mean of the reference group is denoted by the intercept, right? So if I kind of look back up here, mean for males, 25.55, 56. Let's see the same thing here with some rounding error. And then the difference between females and males is represented by that coefficient. And the p-value and the t-value are exactly the same as up here, right? T-value of 0.826, p-value of 0.411. So just a little refresher on t-tests, you're gonna have to do that this week. So I'm basically gonna give you some data, say, okay, here's a two group scenario, run a t-test, then put it into the regression context and compare. Then do the same thing with multiple grouping variables. So pay attention. You're going to want to start to pay attention to and get a feel for, when looking at how a variable is coded in SPSS, how is SPSS going to choose the indicator variable? What's the equation going to look like? Because the following week, it'll be important this week, but starting in week 8, it's going to be super important. And you can get a little bit confusing. So part of this week is you can kind of work up to that too. All right, so that's all I have. I'm happy to go through another example or go back to last week. What do you guys think? It seems to me that you probably are enjoying having the recording and going back and
Yes.
I know that from prior experience. That's one reason. That's one reason why I kind of am favoring the Zoom for this, because we can do that in the classroom kind of, but it's almost like it's better for all of us if I record this way. And then I know, because during the pandemic, this is how we were doing things. Everyone was like, no one recorded lectures before. Or else